This is a message from PaulGradenWitz today. He says he has a problem with my rulers and what that would state. That's basically my discussion has been that with the Schwarzschild metric, at least, it describes a systematic error in measurement. Basically, Schwarzschild metric says it says c squared d tau squared equals 1 minus r sub s over r, all this stuff here. And my basic point was essentially that the correct measurement, the correct measurement of time would be dt. The incorrect measurement of the time is d tau. The clock here, if we just have, if we don't have it moving in the space, then r is not changing, theta is not changing, phi is not changing. We just have this part. And this is the correct amount of time that has passed, the dt. And this is what the clock actually measures. And the correct amount of time that passed is just that. It's the correct amount of time that passed. And this is what the clock measures. It's incorrect. So this is describing an error in the measurement. It's not, it tells what the clock says, but it's telling you how what the clock says relates to the correct passage of time. Similar thing can be done for s squared equals, fix it this way. I'll erase this s squared here. ds squared equals, and what we're going to do is change the positives to minuses, negative this, plus this, plus this, and then we've got the space-like time-space interval. And in this case, what we've got is, if we, let's say we just have a ruler in the direction, in the radial direction, then we can say that we can cancel the d theta. There's no d theta there, it's just going out radially. The d phi, and we can cancel the d tau because we're just having the simultaneous events attached to the ruler. And we can see that ds squared is equal to this term times dr squared. And this also, the dr is the correct measure, and ds is an incorrect measure. It's incorrect, but it is what the ruler actually says, assuming, of course, that Schwarzschild metric is actually valid. I'm not as confident in this part of the Schwarzschild metric. I have not ever been convinced that this coefficient actually belongs here. But if it is correct, then this indicates how the actual ruler measure compares to the true measurement of the radial distance, different dr. So I just wanted to go back to that to say, to clarify this, since Paul said he had a problem with my rulers and what that would state. So I just wanted to give that more clear. So let's go ahead and continue reading. Let him give me an example of how to find if there is curvature on the surface of the Earth. You take a point O, so I'll draw a circle. I'll say this is point O, and there you let 3 lines go out over the Earth. So maybe like this and this. These will meet back here. And this, oh, this should meet together back there. And maybe this one. We've already got one of them drawn. Actually, we could have used one of these points and we'd already have that circle drawn. And we'd only need to draw one more circle. That would be 3, right? Okay. Um, the angle between the three lines is 120 degrees. Okay, so in essence, we're going this way, and this way from the point O, so that they're 120 degrees each. And at the end of these three lines, A, B, and C, you connect these three endpoints with the shortest possible line to the other endpoints. So the shortest possible line for each of those is going to be, I think, would come up kind of like this, wouldn't it? They'd be, I'm not sure. Would they look round that way? Which way would a great circle go? So, I don't know how to draw that three-dimensionally. Maybe I ought to take it to Mathematica. Okay, yay, I've got a sphere. Now where do I go from there? That's a tricky one. Well, I know that I'm gonna want a circle, right? So I will type circle and then look up the information about what its syntax is. Maybe I can figure it out from there. It looks like my options might be Bezier curve and B-spline curve, maybe. So this is what a three-dimensional B-spline curve means. Interesting. I don't know for sure that that gives a circle or how that works. Here's something that looks almost like a circle, but I don't know if it's exact. Let's grab it. Okay, the B-spline curve created that black curve, and the regular circle created this red curve. I can't tell for absolute certain, but I think it's not quite circular. And anyway, it isn't giving the, yeah, there's definitely comes out a little further there and goes in and then goes out and goes in. So that's not a circle. Oh, I'm remembering how to do this. Yes. I'm going to go with my old standby, the parametric plot 3D. All right, we're going to go with a sphere point function. And the sphere point is going to be a function of r theta phi, and it's going to go, r sine theta is going to be our z, and then our x and y are going to have a component of r cosine theta, and then x is going to have cosine of phi, y is going to have a component of cosine of phi. And then we're going to have three lines coming out of here. So our first is 1 comma theta comma 0. The second one is 1 comma theta. It's going to be 1 comma theta comma and then not 0, but we want it to be 120 degrees out. So 120 degrees times pi over 180. Over, yeah, 180. And the last one is going to be sphere point 1 theta, and this one's going to be 240 times pi over 180. 240 times pi over 180, right? To make it 240 degrees. And then we want theta to go from, this is the parametric part, we want it to go from 0 to, say, pi over 6. And will that work? Well, it did something. I see 2 of the arcs. Where's the last one? And they're right across from each other. That's weird. They should have been 3 of them, and they shouldn't have been exactly opposite. Did I seriously mess that up again? Is this supposed to be cosine? And this is sine? And this is sine? Oh. Okay, there it is. R sine theta cosine phi, r sine theta sine phi, and r cosine theta. And I think this is actually correct. It looks really weird though. Let me actually make theta go from 0 to 2 pi and see if that looks less surprising. Does it look like, man, it still looks really weird. Maybe if I put the sphere in there with it, it would look better. Okay, I think I see why it looks funny, because the graph was put on something that didn't actually show the entire spherical region. So let's fix that by saying spherical region is true and see what that looks like. I would say that looks better. Yeah. So that makes it look better. Okay, and here it is with just those things in there. And oh boy, it's going to be a trick to get the circles areas in here and here and here. But let's just draw like that for now and see if we can sort of get an idea. Where is that going to come through? It's my intuition is not good on this, but I feel like if we draw it here, it would look like a straight line. If we draw it here, we're going to have sort of outward direction around each side. But what I want to be careful of here is if I draw this, I don't want to draw it because I think Paul is taking into account great circles rather than what do you call them? Latitude lines. Because this equation is going to work great for drawing latitude lines. I could do that without any problem. Question is whether I can draw great circles on it, which is going to be higher math. Could it be like solving a Rubik's Cube? I want to draw a line from that point to that point. So I will rotate that up to the peak and then rotate this around until it's directly below it and then draw the line right along there. Something like that. Alright, I'll just use this figure to work through the rest of Paul's text to the best of my ability. Take point O, which is going to be here, and you let 3 lines go out over the Earth with a fixed length. At the end of these lines, we'll call them A, B, and C. You connect these 3 endpoints with the shortest possible path. I think I kind of aligned that one so it should be a straight line. And Control Z. All right, things are not working well. Okay, and then this one will come around this way, and this one will come around this way. I'm not drawing those very well. Let's see. Z, undo, undo, and we'll just, crap. This is difficult. Why is it eraser now? Okay, I should just pause and get it done. Okay, we connected those 3 endpoints with the shortest possible line. Those would be great circles. Each of the 6 lines is a great circle. Now you start. So now you start at one triangle point A and take a short ruler in your hand that is parallel to triangle lines A, B. And with that ruler in the hand, go from A to B while maintaining the orientation. At B, you drop the ruler on the ground, rotate in the direction from B to C, take the ruler up without rotation, wait, rotate in the direction from B, huh? You go from A to B while maintaining the orientation. At B, you drop the ruler on the ground, rotate in the direction from B to C, and continue from C to A. Take the ruler up without rotation and continue from B to C. Well, the ruler already rotated. It came this way. So there was a rotation of the ruler there, and then there was a rotation, and then there will be maybe slight rotation there, and maybe slight rotation there. Oh, I've seen this before. Right, because you're pretending there's not a third dimension, and you're pretending that it didn't rotate. Well, it did rotate because you're in 3 dimensions. What was this called? Well, this isn't it, but here's something that one of the early things from 2012, January 14th, 2012. I remember I was visiting my sister and walking around talking to myself until she said I was crazy. But yeah, this was what I was working on that day. One thought experiment that general relativity experts like to discuss is parallel transport. The basic idea is that if I take a pole or physical object and walk around coming back to the same place, and I keep it pointed in the same direction the whole time, then when I get back to where I started, will it be facing the same direction it was when we started, or will it have turned, perhaps even changed its length? Specifically, the example most often used to elucidate this question is an example where 2 dimensions are embedded in 3 dimensions, specifically a sphere. Consider what we live on a sphere, its natural surface to consider. If you tried to walk in a square, travel L units in a straight line, turn left 90 degrees, travel L units, turn left, travel L units, turn left. Now it should be pointed out that this is in fact impossible to travel in a straight line on the surface of a sphere. However, if I try to walk in the straightest line possible on the sphere, there is an unambiguous meaning. As I step forward, my front foot will tilt slightly forward, following the contours of the sphere. There's nothing I can do to prevent that, but I can prevent my foot from angling to my left or to the right. The resulting path is called a great circle. What is a great circle? Imagine splitting the sphere right in two. Half the sphere is to your left and half the sphere is to your right. You want to stay on the path that is right between those two halves. So for any given point, no matter what direction you choose to walk, there is this well-defined path down the middle. This great circle may not be what you expect. If you are familiar with maps of the world of the globe, of course, you see latitude lines going around the globe east to west. These are not great circles. If you ever fly from New York to Spain, you may be surprised to find the plane will fly almost over Greenland. The great circle does not go straight to east to west. To get a more hands-on idea of what's going on here, get out a felt tip pen or blow up a balloon or find a ball you don't mind drawing on and try this on your own. Follow the instructions for drawing a square given above using a small distance, letting the pen travel in a straight line distance, and judge the 90-degree angles locally. You will find that with a small L you will get back what looks like a square drawn on a sphere. However, as you draw larger and larger squares, they start looking less and less like spheres. In fact, you won't get back the same directions as you started. So if you start at the red dot, draw a straight line in any direction. Follow the red line to the orange dot, then the same distance to the yellow dot, then the same distance to the green dot, and the same distance to the blue dot. This almost creates a square if you make the line small, but varies more and more from the square as you make the lengths sides longer and longer. If we increase or decrease the length of each path, this kind of shows what happens as you increase or decrease the lengths of the paths. Then it repeats. Global coordinate systems. How would you describe any point on the sphere? Can I say start at the red dot, travel x units forward, turn left 90 degrees, and then travel y units forward? Is this enough information to establish the location of any other point on the square? I would say yes, but with one caveat. We need to specify the initial forward direction as well. Given the red dot and the red line telling you which way is forward, this is enough information to specify any point on the sphere. Given the red dot and the direction of the red line, we can give instructions to get anywhere on the sphere by saying go straight x units, turn left, then go straight y units. Another coordinate system, there's a much more standard coordinate system that does much the same thing as the one above. Instructions are start at the red dot, move x in the direction of the red line, turn left 90 degrees, then travel a distance y in the direction of the orange line. With those two numbers and those instructions, x, y are sufficient to specify any point on the surface of the sphere. However, we could also give these instructions. Start at the red dot, facing in the direction of the red line. Now turn left by an angle theta. Now walk a distance y. These instructions are also sufficient to specify any point in the surface of the sphere. But a couple of things have changed. Now, instead of walking the distance x, we're turning an angle phi. You don't have to walk nearly as far. So here we're able to still use two numbers to specify the location, but one of them is an angle and the other is a distance. This is still not the standard way of describing location on the surface of a sphere, but we're getting closer. Standard way of describing location on a sphere is to use two angular measurements, phi and theta. How do you do this? You think of the theta angle as a distance instead of a turn, whereas the phi angle is just turns you before you start. The theta angle sweeps out an arc length on the sphere from the North Pole to the South. Okay, so that was 2012. Parallel transports in Warwick. This is from, what is it? Expressing Einstein notation as matrices, part 5. I have something about parallel transports in Warwick. And the idea behind parallel transport seems to be that we take a basis vector and move it in a direction, and we see what happens to the shape and direction of the basis vector. Of course, if we have a true basis vector, which is defined by the magnitudes of each part being equal to 1 unit, and the units are the same, nothing will happen to that basis vector as we move it all around. But if we have a set of pseudo-basic basis vectors like E sub r, we have to reorient its direction as we move around so that its base always points back to the origin. If your basis vectors are e sub x or e sub y, to keep it parallel when it's moving, e sub x, keep it horizontal. Did you really keep it parallel? That probably depends on whether you use the planet's surface to define horizontal. If you did, then no, you didn't really keep it parallel. Again, e sub y depends on whether you use the planet's surface to define vertical. Unit displacement, how to keep it parallel when moving it? E sub r, keep it pointed directly away from the origin. Did you really keep it parallel? Definitely not. Unit displacement E sub theta, you would keep it pointed directly perpendicular to the origin and stretch it so that it spans an arc of 1 radian around the origin. And did you really keep it parallel? Definitely not. Gravitational field, how to keep it parallel